Let's see the guidelines for the voltaic cell. So we have the whole curve which applies. Cathode will undergo reduction, anode will undergo oxidation. Now the cathode is going to be positively charged, so it's the positive electrode in a voltaic cell, while the anode is the negative electrode in the voltaic cell. The more reactive metal will have greater tendency to lose electrons. Therefore, it will undergo oxidation. So this is very important. The more reactive metal undergoes oxidation, the less reactive metal undergoes reduction. And electrons will always flow from the negative electrode, that is from the anode to the cathode. So always from negative to positive. So bearing this in mind, let's see the simple voltaic cell, the Daniell cell. So the Daniell cell consists of a zinc half cell and a copper half cell. So the first step is for us to determine where oxidation takes place. So oxidation will take place where you have the more reactive metal. So zinc is above copper in the reactivity series, therefore zinc will undergo oxidation. So oxidation means that it's going to lose electrons. So this is why we can write Zn solid giving electrons, and this shows that the zinc electrode is dissolving because we have the change in state from solid to aqueous. So this is showing dissolving of the zinc electrode. As it releases electrons, it gives a negative charge to the anode. So here this is dissolving, so it's going to be eaten away. We can say it's eaten away. So this is going to become, so you have buildup of electrons in the anode here. So this is the anode and this is negatively charged. On the other electrode, you're going to have reduction. So copper is less reactive than zinc, therefore reduction will take place. So it's going to gain electrons and form copper solids. So you have the gain of electron and you have the change of aqueous to solid. So copper ions are used up and copper metal is being formed. So here you're going to have electrons being used over here. So the overall reaction is where you have the zinc dissolving to give Zn2 plus and copper 2 plus absorbing the 2 electrons to form copper solid. So the overall reaction, let's just add these two equations. The 2 electrons cancel out. So you have zinc solid plus Cu2 plus aqueous. This is producing zinc 2 plus aqueous and copper solid. So this is the overall reaction happening. The salt bridge completes the circuit, allows the flow of electrons. Electrons flow through the circuit, causing an electric current. A potential difference is generated between the electrodes, which is shown by the voltmeter. So because you have the flow of electrons from the anode to the cathode, so flow of electrons always from more reactive to less reactive. And as the redox process occurs, the blue color of copper sulfate fades, copper bar increases in size and becomes coated with all copper, and the zinc bar gets thinner. So this is what I was saying. So the zinc electrode is dissolving, so this is going to get smaller in size. And here, because you have the Cu2 plus being used up, the Cu2 plus, this is what gives the blue color. So Cu2 plus is being used up, therefore blue color fades. And because you have the formation of solid copper, you're going to have a layer of copper that builds up over here. So these are the observations that occur during the Daniell cell. Now, if you look at the anode, you have the Zn2 plus which is being formed. So I have lots of the Zn2 plus. So concentration of Zn2 plus here is increasing. Now the role of the salt bridge here is to maintain neutrality. So to neutralize the buildup of the Zn2 plus, we're going to have Cl minus that moves down into the half cell. So it's going to neutralize the Zn2 plus which is produced. So as Zn2 plus builds up, Cl minus from the salt bridge moves down, while Zn2 plus from the solution moves up the salt bridge, maintaining electrical neutrality. And again, on the other side, because you have Cu2 plus which is used up, so here you have an accumulation of SO4 2 minus. This is negatively charged, so the negative charges are going to be moving into the salt bridge, and you're going to have the K plus which is going to move down the salt bridge. So you're going to have neutralization here, so it's going to prevent the buildup of charges. So SO4 2 minus is going to build up, K plus moves down, while SO4 2 minus moves up, maintaining electrical neutrality. Now, instead of drawing the voltaic cell with the half cells and the voltmeter every time, we use cell diagrams. This is a shorter way of drawing the voltaic cell. So there are some rules when you're drawing the cell diagram. The first one is that we use a vertical line to represent phase boundary between a solid electrode and an aqueous electrode. So if you have different phases, you will see a solid line. If you see a double vertical line, it means a salt bridge. So aqueous solutions are placed adjacent to the salt bridge. So you will always find the aqueous solutions adjacent to the salt bridge. So salt bridge, double line, aqueous solutions adjacent to the salt bridge. The anode is on the left and the cathode is on the right. So you will have the anode here and the cathode here. So anode and cathode. Spectator ions are emitted, so we don't see SO4 2 minus or any other ions, any other spectator ions, so omitted. If within a half cell there are two ions, they are separated using a comma. So let's say you had H plus and Zn2 plus aqueous, so then you would have H plus aqueous, comma, Zn2 plus aqueous, let's say. So if you have two ions, they're separated by commas. Let's try this one. So you have magnesium, so Mg solid in Mg2 plus aqueous connected with zinc solid and Zn2 plus aqueous. We have to find which one is more reactive first. So magnesium is more reactive, so magnesium is going to be on the left and zinc is going to be on the right. So you will have magnesium solid separated by one bar, magnesium aqueous, and then you'll have the salt bridge, and then on the other side you will have zinc aqueous, and then Zn2 plus aqueous, and then zinc solid. If we consider silver in silver nitrate and copper in copper sulfate, so here copper is more reactive than silver. So copper is going to be the anode and silver is going to be the cathode. So we'll start with copper first. So you will have the copper solid, copper 2 plus aqueous, salt bridge, and then the silver nitrate, so Ag plus aqueous and Ag solid. Now, different half cells make different voltages. So for any voltaic cell, the direction of flow of electron and the voltage generated can be determined by the difference in reducing strength of the two metals. So based on the position of the metals in the reactivity series, we can determine what voltage is going to be produced. If we have a large difference in electrode potential between the two half cells, we'll have a large voltage, which means that if the two metals are very far apart from each other in the reactivity series, we're going to have a high voltage. So if you look at the activity series from section 25 in the data booklet, so this is part of it, and you can see if you find zinc and you find silver, zinc and silver, there's a large difference in reactivity. So this produces 1.56 volts. But if you do a half cell of copper and a half cell of silver, these two, there's very little difference between the activity of these two. So here you have a very low voltage of 0.46 volts. So here you have high difference in electrode potential. Here you have a small difference in electrode potential. Therefore, you have a smaller voltage. So this completes part 1, where you have the voltaic cells.